We live in a time of global transformation. The Energy Futures podcast explores how we can accelerate the expansion of clean energy technologies and reduce our reliance on fossil fuels. From heating and cooling our homes to moving around our planet and beyond, we bring together researchers, scientists, business leaders, and communicators to exchange knowledge and try to answer one important question. How can we create a sustainable energy future for all? This podcast is produced by Energy Futures Lab of Imperial College London.
What are the key challenges in manufacturing wind turbines? And is the lifespan of wind turbines impacting the sustainable nature of wind farming? This episode is hosted by Dr Aidan Rhodes, a research fellow at Imperial College London, an energy policy fellow at Energy Futures Lab. His first guest is Cristina Fernandez Alonso, a product service engineer and blade project manager at GE Vernova. Cristina specializes in offshore wind operations and maintenance. She also contributes to developing technological training for offshore wind professionals. Today, they're joined by Dr. Sara Jimenez Alfaro, an aeronautical engineer and postdoctoral researcher at the University of Oxford and also Imperial. Her research focuses on the lifespan and deterioration of wind turbines. In this episode, they will discuss the ongoing construction and targets of the largest wind farm in the world, challenges to the construction, operation, and maintenance of wind turbines, innovative research into the lifespan of these offshore giants, wind power as a leading innovator in renewable energy.
So, welcome back to another episode of our Energy Futures podcast. And today we are going to be discussing large-scale offshore wind farms and all the fun technology and advances we've seen over the last few years in the North Sea in England, in the UK actually. I'm Aidan Rhodes. I'm a research fellow here at Imperial College, and I'm joined by two experts in the field who are going to be taking us through the subject of offshore wind farms today. So first is Cristina Fernandez Alfaro. And the second is Sara Jimenez Alfaro. So, Cristina, can I ask you to introduce yourself for our guests and just explain, how you got to where you are?
Thank you so much, Aidan. So I'm very honored of being here at the Imperial College in order to record this podcast. When first I received the invitation, my first nerves were genuinely overwritten by excitement because back in 2012, joining the Imperial College as a semester Erasmus student was among my options. But despite the fact that this option didn't materialize, being here nowadays to talk about Turbine project on behalf of GE Vernova represents a big milestone for my career and a consequence of the hard work and learning of the years.
So, what is your current position at GE Vernova?
So I have built my career as a product service engineer within GE Vernova, mainly focused on offshore wind operations, blade maintenance, and also corrosion management. So my journey began in Spain, where I have learned and I have done a material science engineering degree at UPM, Universidad Politécnica de Madrid. Then I did a semester abroad at INSA Lyon in France, and furthermore, I got a master's degree into renewable energies and energy efficiency. Afterwards, over time, I got involved into projects across Europe because I started working in oil and gas field in Lyon. Later on, I moved to gas turbines to join GE Power in Belfort, France. And due to my expertise into maintaining performance and integrity for the assets, as well as my personal willingness to switch into renewable sector, I got the chance to move to GE Vernova Offshore Winds 8 years ago and to join this challenging department in the Hamburg office in Germany. So nowadays, I have been invited to join this challenging project, the Turbine project, which is a great milestone, not only for our company, but the overall climate change program. So I will start working for this specific project as soon as the turbines are installed. They are done with the electrical and mechanical commission, and then to perform the handover services. So what I really love about, and I'm very passionate about my job, is the fact that it's not only keeping the turbines running to ensure availability, but it's also the long-term cooperation that we establish and we build with our end customer, because we are signing contracts of service agreement maintenance that is lasting longer than a decade. And over this time, and in the front line, receiving technical calls from the field technicians and ensuring that the turbines are not stopped. So I received those problems, those technical challenges in the form of non-conformities or root cause analysis. So I having the impact in a daily basis in the field directly.
Brilliant. And it's interesting that you started off in the oil and gas sector and have transferred over to renewables. So hopefully many other people are considering that sort of career change as well. So Sarah, it's good to meet you as well. So how did you become, I know you are currently a postdoc here at Imperial and at Oxford,
Exactly.
but how did you arrive at that position and what are you currently working on?
Yeah, well, first of all, nice to meet you. As Cristina, I'm from Spain. I started my career journey there in Seville, in the south of Spain. I studied aeronautical engineering, and then in the last year of the master's, I moved to Paris to do the PhD. It was 3 years, and it was an amazing experience at Sorbonne University. I was a part of a network dedicated to study fracture mechanics. It was called NewFrac. And in the last year of my PhD, I was interested in research about renewable energies, etc. I met a professor here at Imperial College, Emilio Martinez Pañeda, and then we applied for a fellowship inside the Energy for Future network that is also inside the Marie Curie Actions, and that's why I became a postdoctoral researcher here at Imperial.
Oh, okay, very interesting. So what is your research, just in the kind of, I guess, terms for the audience?
My research is mainly about the study of fatigue and corrosion. So I'm an expert in fracture mechanics, and the idea is to analyze how computational methodologies in fracture mechanics can now predict the fatigue life, in particular of offshore wind turbines, and how we can enhance this fatigue life that is now 25 years old, maybe it's 35 or 45 years. And one of the main problems of this fatigue life is corrosion. So the idea is to put together fatigue and corrosion and study this phenomenon as a couple phenomenon, how corrosion affects fatigue and how fatigue affects corrosion.
So you're looking at long-scale fatigue. So what would be the average lifespan of a wind turbine blade then? Do we know yet? Is that something?
About the offshore wind turbine is 25 years old, the general estimation, and maybe this is too short. This is one of the drawbacks of these kind of machines. We are talking about the biggest machine in the world,
Yes.
and we are talking that we have to change it in 25 years. A lot of pieces, a lot of material. And the idea is that maybe it's 50 years. No, imagine the aircraft, for example. There are aircraft that has like a lifespan of 50 years or more. So how can we enhance the methodologies to predict this in a better way? That's the main objective.
Okay, so fascinating research. So let's go back to Cristina, because I know you've been working on the Dogger Bank offshore wind farm, as you mentioned. So could you give us an overview of the Dogger Bank project and why it's so significant for the UK green energy sector?
So Dogger Bank Wind Project is not only fascinating because of its size, but also because of its location. We are targeting to build the world's largest wind farm in the world, and this is mainly built on top of Doggerland. Doggerland used to be a land that connected Great Britain with mainland Europe during the Ice Age. But then gradually over the years, due to the fact that the level of the sea level was rising because of the glaciers got melted, then it was swallowed. So it's really poetic. It's a meaningful impact into the climate change, because we are going to combat a man-made climate change by installing a 277 Haliade-X wind turbines offshore on top of the land of Doggerland. So this exciting project, I'm sure that you have heard those numbers before, but those next generation Haliade-X 30 megawatts wind turbine that GE Vernova is providing have blades that are 107 meter length. They are manufactured with new technology of composite materials. We are talking about carbon hybrid materials, which have a better weight-length ratio for the better performance. We are also targeting one of the most efficient turbines in the world, because they have a capacity factor targeting 60 to 64%, while the predecessor offshore wind turbines, we were in the range of 40 45 to 50% capacity factor, because larger rotor, that is 220 meter rotor diameter, means larger swept area, so then we can produce better or more quantity and in a more efficient way. This capacity, this wind farm, will be able to provide enough electricity for an estimated 6 million UK houses with these massive 277 wind turbines. So this means that with one spin, we can provide electricity, green energy, to a total number of 2 houses for a day. So definitely the Dogger Bank example is showing us that large-scale offshore wind farms are nowadays a reality.
And of course, just for our listeners, the power output of a wind turbine is related, I believe, to the cube of its diameter, is it?
Well, yeah, partly correct. The idea is that you change the moment of that you have, the forces, in energy. So
Yes.
yeah, if you have a bigger blade, then you will be able to produce more energy. So it's related to somehow.
Substantially more energy.
Yeah.
So we are talking about a swept area of nearly a quarter of a kilometre, over a quarter of a kilometre maybe. So this is really quite substantial work. I'm going to come back to Sarah and talk about some of these new advances in material science, which Cristina pointed for the wind turbine blades. When you consider stuff like fracture and so on, what sort of, material properties are important?
Okay, in terms of fracture mechanics, you mean? Okay, well, normally we take into account what we call the fracture properties. So, for example, one fracture property would be the fracture toughness, another one, the tensile strength. If we are talking about plasticity, maybe we consider the yield strength. So those magnitudes, the yield strength would be the first strength at which plastic deformation starts, and the tensile strength, the strength at which we will have fracture, crack nucleation, or propagation. In terms of materials, normally we talk about materials that are ductile or brittle. If the materials are brittle, it means that they don't have plasticity before failure.
So they sort of snap.
Yeah, and in terms of ductility, maybe they are more interesting in, cars, for example, normal cars, because they can deform, they have plastic deformation before failure, whereas brittle materials, maybe they have other applications like Formula One cars.
Yeah, okay, very interesting. Come back to you, Cristina. So I know Dogger Bank, a very large-scale project, and it wasn't just your company which delivered it, but several major players. So could you discuss how this collaboration between the various project partners worked and how it influenced the design and execution of the project?
Sure. So Dogger Bank is a clear example what a very high collaboration and international level means. So we are talking about a joint venture where it is led by SSE Renewables, by Equinor, and by Vanguard, and also GE Vernova is providing the wind turbine technology. So our company is providing the 277 Haliade-X, so next generation offshore wind turbines that will be installed in this wind farm. So definitely it was a major challenge to align all the stakeholders from sourcing department, from logisticals, from also local authorities. So everything needed to be very tightly coordinated and all the messages communicated in a full transparency in order to ensure the timeline of the project. So each partner is bringing here main key values to the table. So from one hand, we were bringing the technical expertise, so cutting-edge technology with one of the most efficient wind turbines in the world. On the other hand, they were also bringing economical power and also local regulation and expertise into UK standards. So all that generated a project into a health and safety very strict framework, which is good because in our company, our first policy is safety first. So we are taking very seriously the safety in all of our operations, not only in installation, but also during construction and also during the operations and maintenance that is going to take several years. So ensuring this lifetime that Sarah mentioned before, that is stipulated of 25 years for our wind turbines. Just to put an example about how those logistics work, our nacelles, which are the big house that is installed on top of the tower, so just behind the rotor, that is here, we are in London, so those nacelles are larger than one red bus that you have here in your city, and it has 600 tons of weight. So one of those nacelles takes up to 3 days sailing from Saint-Nazaire factory in France, from GE Vernova factory, all the way down to the port in Teesside in UK. So meaning that there's a huge infrastructure, a very well organized logistics setup in order to ensure the delivery of the material, the load out of all the nacelles and of the turbines, where they will be then stacked together at port in UK with the blades that are coming from Cherbourg, France, and also the towers that are traveling from Portugal. So it's an overall very complex operation and very complex project, but with all those stakeholders heavily involved and good alignment, we are ensuring the success.
So basically, all of the blades and the nacelle and the towers all come from different parts of Europe and are transported by ship, are they? Correct. And to Teesside, where they're assembled into a final well. So how do you get the blades across? Because, as you say, they are over 100 metres long. Is there significant logistical challenges of transporting those?
Correct. So we have special vessels, special transportation vessels, and that's why also our factories are directly on the port, because we cannot travel over the road. We cannot go over roundabouts. That would be impossible. So we need to go directly from port to port in order to ensure these logistics and to avoid any kind of damages, because those blades that are made on hybrid carbon composite materials are very fragile as well. So we need to take care of all those logistics, of all load out, in order to ensure that no additional defects are happening during this transportation phase.
Okay, so it is an extremely complicated system which you have to repeat over 100 times.
It is very well controlled.
So I'm going to come to Sara. When you work on offshore or on offshore wind turbines, what are sort of the key challenges you've seen come up again, just generically?
Well, many challenges,
yes,
I think.
Of course.
In terms of the loading, since the size of the wind turbines, they are growing. We are facing new kind of loading. For example, they are surpassing the first atmospheric layer. Yeah. So we are changing the loading profile, and that means that we maybe need to change our designs in order to withstand those loads. And another one is that since the towers, they are becoming big and big, now that they are waiting in the quayside until they are installed, they can suffer from a phenomenon that is called vortex-induced vibrations. There are some vibrations that can affect to the fatigue life because they introduce some additional damage. So those are just two challenges among the big list.
Yeah, and I guess we are seeing these are becoming giant structures now.
Yes.
And basically the ability of, because I've also heard that another challenge is as the wind turbine gets faster, you head towards the sound barrier and things like that at the tip of the blade. But
yes, exactly. Yeah. We are talking about a machine that is bigger than the A380, the Airbus, the biggest plane. So yes,
as you say, the largest machines in the world.
Yeah, rotatory machine. Yeah.
I'm going to come back to you then, Cristina. So obviously we've heard some of the generic challenges, but what were some of the specific challenges that your company faced in installing these giant wind turbines?
So as any mega project, Dogger Bank presented massive challenges that we overcome, thinking out of the box, with the principle of delivering in an uncertain world. So mainly we face problems with logistics, as you might know, all the geopolitical situation, additionally with the pandemic, those were not easy moments. So definitely we need to secure that key materials were available on time, or otherwise to build some contingency plan in order to ensure that the load outs of nacelles, towers, and blades was still ongoing. On the other hand, we have also the challenge of the location. So we are talking about a wind farm that is installed 130 kilometers from shore, from Teesside in UK. So therefore, this presents major challenges, not only for the logistics of transportations of the towers, nacelles, and blades, but also for the installation, the construction, and also later on for the operations and maintenance that are right now ongoing. So those require specific logistics, which means the introduction of service operation vessel, SOVs. These kind of vessels, they can drive at around 12 to 13 knots, and it will take to them 5.5 or to 6 hours to reach the offshore wind farm. So it takes a long time to reach that point. So in order to make it more efficient, our setup is we are not sailing there daily, which means that we are keeping the service operation vessel in the wind farm for a total length of 2 weeks. So it means that the vessel is only traveling to port once each 2 weeks, which minimizes the traveling risk, with optimize the time of our technicians on the field, so meaning ensuring 12 hours on the wind turbines that our technicians can do the maintenance. So this reduces the downtime. Additionally, regulatory framework. So we had a lot of concerns and safety and environmental problems in order to get the permitting to work. So that was a full coalition with legal entities, with local authorities, in order to ensure that we will get the right permitting to move ahead with the project. So just an example, the first load out of our first 6 Haliad X nacelles happened the 15th of June of 2023. This is a date where we celebrate the Wind Day. So it's a key milestone that we target that day, because we are celebrating how powerful is the introduction of the wind energy, so green energy, into the market in order to decarbonize the emission, to reduce CO2 emissions into the atmosphere, and also to make the grid more stable and to maintain the prices of electricity affordable for everyone.
So so just to give our listeners a viewpoint, what was the time frame? Because you mentioned the pandemic and various other geopolitical situations. So when was work started on construction of Dogger Bank, and when is it going to be finished, or has it been finished already?
So we have a very aggressive KPI, key parameter indicator, which means that we are committed to finalize the installation within the year. So by the end of 2025, the first phase, okay, we are talking about a project that has 3 total phases, Dogger Bank A, B, and C. So Dogger Bank A, that is a total number of 95 wind turbines, will be finalized by end of the year. Nowadays, we have installed 54 turbines. They are still in installation, not finalized, not hand over to services, but the progress is positive. So we are moving ahead with this tight schedule and also hitting all our commitments.
Okay, interesting. And you started when?
So the first nacelle arrived to the port in October 2023.
Oh, right. So very quick, actually, the construction has been.
Well, very quick. It's a long-term project, so it's not going to be very quick. The 3 phases is expected to be run about 5 years installation. Okay. We don't know yet, but yeah, indeed, we are fulfilling the KPIs and delivering the turbines at the time that we committed with our end customers.
Brilliant, thank you. So we're now going to talk about, I think, maintenance, because as you mentioned, Dogger Bank is 130 kilometres from shore, and this is not an easy thing to get to. So I'm just going to come to Sara, because I know that you've done a fair amount of work, where you've done a fair amount of research on these long-term maintenance issues, these fracturing and corrosion. So what sort of, how do you monitor the state of a blade? Is there sensors on the blade, or is there computer models you use, or digital twins?
Well, I work mainly on towers, not on blade exactly, but it can be applied also to blades in the end, because we are talking in the end about materials and structures, so it has to be the same, no? But the idea is that you apply a computational model on the structure, blades or towers, and then you know when the cracks are nucleated. So normally these kind of structures, in terms of tower, maybe not for the blade, they have some roughness. So those cracks appear on the surface, and then they nucleate. They nucleate because they propagate because of corrosion, and then the failure appears. So we don't exactly monitor when to maintain that. We measure the fatigue life of those structures.
So you basically measure the fat heat life, use a computer model, and then go, this is probably needs to be looked at.
Method. Yes, exactly. Fracture mechanics methodologies to predict the fat heat life, not exactly to predict when to maintain. I think that Cristina knows much more about that. My idea is how to extend this fat heat life from the scientific point of view.
So how would you do that then?
The idea is that nowadays they predict the fatigue life using very simple methodologies, in my opinion, because they just take a specimen, they go to the lab, they build the so-called SN curve, where they face the stress, the amount of load they are applying, with respect to the number of cycles that this specimen needs to fail. And once they have this, they take into account all the effects that we can have in a wind turbine, like roughness, as I've said, maybe this is more for the tower, or corrosion or other kind of phenomena, just applying a correction factor that normally is around 3. And this is how they change the curve. So in the end, you end up with some empirical relationship. And what about, instead of having this empirical relationship, using computation, using multiphysics problem to combine everything in a finite element code and to predict in a more accurate way this fatigue life? So using the real structure, using finite element method, using the fracture mechanics methodologies all together to really have an accurate prediction of this.
Okay, very interesting. So it's quite a lot more complicated than the traditional models then.
Yes, of course. And I think one of the big challenges is to put everything together, to combine all these multiphysics and to understand how they work together, how they can interact, for example, corrosion and fatigue.
Yeah. Absolutely. And these are very, very aggressive environments, aren't they? We are talking about 130 kilometers offshore in the middle of the North Sea, high winds, of course, high waves, lots of salt corrosion.
Exactly. Many things ongoing at the same time, the corrosion as well because of the seawater. So, we can also have storms or other meteorological phenomena that can affect. So, very complex.
Yes, and of course, in winter maybe even freezing ice and that kind of thing. Absolutely. Yes, no, it is a very extreme environment. So I'm going to come back to Cristina to ask about that maintenance, because you say your company will be responsible for the maintenance of the turbines. Is that correct? Over a period of 10 years. So how do you monitor the turbines and prepare maintenance schedules?
So our maintenance schedules are very thoroughly planned in advance, meaning that we have the preventive maintenance campaign that is having a periodicity of 12 months, and then we are having troubleshooters and also a corrective special maintenance campaign. So the preventive maintenance campaign that has as ultimate goal to keep the turbine running is happening always during the spring, summer season, because during those times we can ensure that we can still guarantee availability, meaning there will be less wind, so there will be less megawatts that will be lost into those months. So that's why we stop turbines during that time of the year to conduct the preventive maintenance campaign. Also, those preventive maintenance campaigns have as input digital data. So here we are introducing the new technology, the third generation turbines for offshore wind. So this means that we are implementing tools like digital twin, which means that over sensors we can reproduce a physical asset, but to monitor there at distance. So if something is happening, we will trigger an alarm or sensors, and we will receive that feedback and that data. So this is really valuable in order to plan our maintenance, because we can plan ahead something is critical or that will stop the turbine to provide the remedy as soon as possible. So these kind of methodologies are key. And also, since you were asking before about the blades, we have also the ICP, individual pitch controller. This means that each blade is equipped with different sensors, which allows the blade to position, to change the angle individually. So not all the blades at the same time, but each blade is changing the angle individually. And this will reduce the loads not only on the blades, but also on the tower, also on the main shaft and on the rotor. So this is a key parameter to monitor and to get this data useful to plan our maintenance in advance and to keep the turbines running as much as possible. This has also an impact into the lifetime of the components, because while you are optimizing the angle of your blades to generate the better output, you are providing more efficiency on your turbine, and you are also maintaining a speed on the rotor, which means that the grid is fluctuating less and you are having less risk and less impact into your asset. So you are ensuring the lifetime over those 25 years that we said before, or even longer.
Okay, so that's very interesting. So this turning of each individual blade, this altering of the pitch of each individual blade, is that something done automatically by a computer, or is that something set by an operations manager?
So the sensors are set up and they are pre-installed in the blades as soon as they are at the factory, and then we need to do this electrical mechanical completion, which means that all the cables need to be connected into our SCADA data system, and then we can retrieve the data online. So nobody needs to be checking or monitoring that daily, because we can get alarms in case that something is happening. But it's an automatic system. Yeah. So this pitching operation is happening on real time on the turbine in an autonomous way.
Excellent. Okay. And just to finish off, you mentioned before that your maintenance vessels require about 5-6 hours to actually get to the site itself. Mm-hmm. Is there helicopter access as well in case of super emergencies, or is the only route with this long sea voyage?
Sure, indeed. Our service operation vessels, they have also a helipad, so they have the space in order to get the helicopters land there, or to have people going down there. So definitely the helicopter is the quick evacuation means in all of our risk assessment. It's incorporated, and also in case of having any casualty on the field, we are not going to wait for 5 hours or 5.5 hours to release that casualty to the shore. There is also another additional mean, not only the SOV, the service operation vessels, and the helicopter, but there is also the CTV. CTV stands for crew transfer vessels. Those are smaller vessels, so therefore they are faster. So with those kind of vessels, we can go up to 20 knots speed, and then it will take us to round about 3.5 or 4 hours. But it's more uncomfortable. It's going to be a more bumpy travel there.
North Sea is often not very flat. No.
It could be very rough, and we have also to take care about the waves. Usually you have a stronger limitation, so you cannot, with very high waves, to reach the wind farm when you are transferring with those crew transfer vessels. Whether with the SOV, you have less limitations, and for example, with the helicopter transfer, you will have no limitations in terms of waves. So indeed, when the waves are very high, that's the only access mean that we might have.
Yeah. Yes, I mean, it is a almost unique site for a power station if you think about it, and with a lot of unique issues. Dogger Bank's obviously been a major project, so what have been the expected long-term benefits, do you think, of Dogger Bank for both the local community in Teesside and the broader energy landscape in the UK?
The advantages of this massive project in Dogger Bank are very large. So initially, we are targeting to create in UK a big impact. So this is by creating around about 400 jobs based in UK. And this is not only referring to the construction or installation phase, but as we discussed before, there will be long periods of preventive maintenance campaigns all over the lifetime of the wind turbines, expected of 25 years. So we will be hiring manpower, local manpower, technicians, technical, competent people to go there and to support into this challenging project. So thoroughly over the years to come, this will generate a lot of opportunities, but it's also a very beneficial project into the overall energy strategy. So we are targeting to build the largest offshore wind farm with the most efficient turbines up to date, and this will generate also knock-on effect into the market, so just to motivate other countries and other OEMs to do the same kind of projects, so to bring green energy into the grid, because it's important to contribute to this climate change, to combat to this problem, and to have broader options for a more sustainable future together with more and higher performance energy solutions.
So quite a lot of excellent benefits then.
We hope so, yeah, indeed.
And then I guess just to finish off, so I'm going to come back to you, Sarah. So talking about sort of future large-scale projects, what has your research suggested people like Cristina should be taking into account when planning future large-scale offshore wind projects?
Okay, yes. First of all, I think that one of the main things to take into account is the computation and the cost of computation before experiments or after experiments, depending. That the fact that we have now new technologies to use it to model maybe bigger structures and to put maybe more complex models and more complex loading profiles, etc. And another thing that we need to take into account is that nowadays we have very good models and we need to combine them together. So, for example, we need to mix fluid mechanics and fracture mechanics, corrosion and fatigue, all of the physics that are in a very huge problem, such as the wind turbines of Dogger Bank. We need to model them in order to design them correctly. Would be my opinion.
Yeah, so basically what you're saying is that convergence,
the convergence, yes, and the consideration of high technologies in order to use them to predict things in a better way and to enhance the accuracy of our predictions.
So basically, more complex modelling, more complicated, complex computational issues. As you're bringing in a combination of structure and atmospheric physics and all that sort of stuff. Yeah.
Increase the difficulty of the problem.
Increase the difficulty, but presumably increase the advantages as well.
Of course, and the accuracy.
Yeah, and just to finish off with you, Cristina. So, what lessons have your organisation learnt from Dogger Bank, which can be applied to future large-scale projects of this? What's the big takeaways, I guess, from this project?
So Dogger Bank project is definitely a rich project and a good example of a lot of lessons learned. So I would like to highlight 3 main takeaways. That would be the importance of deep collaboration, also the use of data integration, and resilience. So if we start with deep collaboration, it means that all the partnership of the stakeholders from logistics, from operations, from maintenance, from construction, installation, and local entities, they need to be well aligned in order to ensure the timeline of the project. This is crucial because if this message is not well transferred, if we don't break down all the steps of this project, the success could be compromised. Then the integration on new technologies. We are talking about using digital twins, predictive maintenance. These kind of new tools are a huge potential for the development of the preventive maintenance campaign. We can bring another example here to the table when we are talking about smart bolts. Those small smart fasteners are different from the old ones that they need to be torqued and retorqued by operators because they have ultrasounds. And with these kind of sensors, with ultrasonic sensors, we are capable to monitor the preload and to ensure that the torque values are within tolerances. So the accuracy of those measurements are around -+3%, which are certified and approved by DNVGL. So this gives us more accuracy and also a better overview about what is the status of our fasteners. We can predict when those fasteners are going to be loosened because we can monitor that in real time, in distance from our computer. We don't need to send any technician there with a hydraulic key or a tensioning device in order to maintain them. So this is less risk and also safer means because we don't need to send a technician, a person that could be put his life in danger because of doing an operation and maintenance of high risk for a structural fastener. Also, for the blades, that was the same. So this we have a blade monitoring system. Those are special sensors installed on the blades that are capable to measure torsional loads. So this is also in order to ensure if we have any deviation, any kind of defect, imagine a lightning strike impact after a thunderstorm. So we can monitor these kind of events. And furthermore, the fact of having this resilience, meaning that over the project execution, we have so many challenges that we need to overcome. For example, the lack of materials because of geopolitical reasons, the pandemics. So we need to be very resilient and to help each other, to have this deep collaboration among all the stakeholders to make sure that we are having the right contingency plans in order to ensure the availabilities of equipment and ensuring the right loadout to continue with the execution of the project. So I think those are the goal rules that we can learn from a Dogger Bank project and the main takeaways that I can highlight.
Okay, thank you very much. So the main takeaways seem to be large computational modelling before we start and a lot of digitalisation and high high amounts of collaboration as we go in order to make sure that we can run these things remotely. So thank you very much to Cristina and Sara for their input today and our excellent conversation, and thank you for listening.
Thank you for tuning in to the Energy Futures podcast. Here at Energy Futures Lab, we are dedicated to addressing global energy challenges through pioneering research, innovation, and advocacy. To learn more about us and the exciting projects we are working on, visit our website and follow us on social media. If you enjoyed this episode, please like and share and subscribe to stay up to date with our latest content. Until next time, stay curious.